Today we're going to answer the question, why does phase lag equal losses rather than phase tangent? So let's take a look at this question. So we know that the dielectric loss, and we're going to concentrate on describing the dielectric loss first. The dielectric permittivity under constant stress is going to be an imaginary number, and it has components. I'm going to leave out the superscript capital X, which represents the permittivity under constant stress. We're just going to use this permittivity is equals to permittivity, which is a real component, which has one prime minus I times the double prime. And you know, the energy stored in a capacitor is 1/2 CV squared. And this C actually is an imaginary number because it's proportional to the permittivity, which is imaginary. Or rather, it's a complex number. So the imaginary part, we said, represents losses, and the real part represents the actual energy stored. So if you're going to apply a voltage over a capacitor, you're going to have some of that energy stored and some of that energy dissipated, and this is understandable. Back to the question which we wanted to ask: why does phase lag equal losses? So what do I mean by that question? I mean that we find in the experiment, when we apply a sinusoidal voltage over a capacitor, which can happen to be PCT or other piezoelectric material of your choice. So when we apply voltage over the material, we will find a phase lag. An oscilloscope is not necessarily the best tool to use here, but I'm just going to draw the phase lag here. So there's some phase lag between the maximum points here. So if the voltage was written like this, the resulting current, we'll call that I, would be minus this delta. And I basically said this in another lecture, but I'd never proved it. So today I'm going to prove it to you that this delta here is the same tan delta prime, which is equal to the imaginary part divided by the real part of the permittivity. So I'm going to prove that to you right now. This same temp delta is related to this delta here, and remember that for tangent of any function, call it x, is equal to x if x is small. If x is much less than 1, then tan x equals x. Therefore, tan delta, this is delta, comes out here. So if we want to describe the energy in piezoelectric materials, so we have this 1/2 CV squared, right? CV squared. And we said that capacitance is a, so you could say complex capacitance, which has a real and imaginary part, or a stored energy and a lost energy. And this should also then reflect into a imaginary stored energy, or imaginary energy, which the real part would be, or sorry, complex, which the real part would be the stored energy, and the imaginary part would be the lost energy. So if we continue and we write this out more explicitly, we'll have the real part minus I, and this is just traditionally the way we're writing these imaginary and real parts, and this is imaginary, so, or you can have it positive or negative, but the fact whether it's positive or negative doesn't matter. So we'll have our capacitor, which had 1 prime, which is a voltage stored, minus I, which is the 1/2 then C double prime voltage squared. And you see how I just basically rewrote this in the form of the same form here. As we're going to see in a couple of minutes or seconds or whatever, this imaginary terminology in this method is sort of a mathematical tool which helps us model actual physical behavior. So keep that in mind. So here we have these two equations, and I mentioned before that tan delta, we don't have to use prime, but anyways, equals the epsilon this. So we could also say that it equals the capacitance, because the capacitance are just related by geometry, and you know, 1 over the other equals 1 over the other. So these relationships are true. So basically, if you multiply C prime by tan delta, you get C double prime, and this is just by multiplying this side on that side. So essentially, we can rewrite this part of the equation by grouping terms. And here we have this. But look here, these are all like imaginary terms. Okay, and what does imaginary mean in real life? It doesn't really mean that much. But what we have to do after we did our manipulations, which imaginary numbers are really great for mathematical manipulations, but you need to go get out from mathematical side of things and get into what's actually happening. So then what we do here, if we want to get in the real world, we want to then mimic, or not mimic, we want to then decide how the amplitude and the phase of this function. So all imaginary and real combinations, we can think about them. I'll just go to another slide for a second. We can think about them as having a phase and a magnitude. So for example, I'm drawing a real and imaginary plot here. So here we have real, and here we have imaginary. So we have a number looking like this, and you have a phase angle here, and real imaginary portions here. So we have a real portion, I'm just going to call it UR, and we have an imaginary portion, which we're going to call minus UI. So the magnitude of this, which I'm going to call U absolute equals the square root of UR squared plus UI squared. And the phase, this phase angle, is going to equal tangent minus 1. The angle is going to be UI divided by UR. And this will give a negative number here, this tangent, which means the angle is negative from the real axis. So this is how we can relate a imaginary number into a magnitude and a phase. And we initially described voltage. You know, this is referring to a sinusoidal case, because only in a sinusoidal case can you really distinguish the phase. The phase does exist, but you can't really distinguish it if you're just applying a pure DC case, like you just applied a step voltage. You won't see this phase phenomenon happening so clearly. And the reason is, as I'll be describing. So the voltage applied in this part of the problem, the voltage applied, and I'll probably just erase it after I write it. The voltage is time dependent. As you can say, this is time dependent, and these energy terms are now also time dependent. The voltage equals sine omega t. You can say multiply by some amplitude, and therefore the energy stored would equal sine squared omega t, and we're going to claim it also has some phase to it, or perhaps you can call it delta, multiplied by 1/2 CV squared. Okay, because that's the relationship. So we're going to have our voltage here, and we're going to have our energy stored. Its energy is always positive here, because energy stored is always going to be positive. It's not going to be negative. So this would be the energy stored, this would be the voltage applied, the sinusoidal would be the voltage applied.